Hello and welcome. In this video, we're going to take a look at the software design process, or sometimes referred to as the software design method. It's essentially a collection of steps or suggestions or process, if you would, that will lead to better quality code. And the intention here is that we make you better quality programmers, better quality developers, and better quality software engineers. Now, this video assumes that you've had an opportunity to work with some languages, perhaps MATLAB, C, Java, JavaScript, Python, or any of the other languages, but we will not be focusing on coding in this video. We're going to have some basic examples, but really the intention of this video is to talk about the process of software development. And so to start off with, we will simply ask the question, why have a software design process? Well, the idea here is that you want to ultimately get more repeatable, more consistent, better quality code. And let me give you a scenario real quick. Let's say, for instance, that you have been presented with a problem or a project for which you need to create a solution. And perhaps you are dealing with a client or a customer that doesn't necessarily know exactly what they want. And so the idea here is that we want to be able to take a large, rather nebulous or poorly understood problem and then systematically break it down to be able to create a good quality solution or a good quality result. And so essentially, you want to think of the software design process a little bit like other methods that you've looked at for general problem solving, except specifically applying it to software. So there's going to be some modifications, if you would, to that general process. And so the idea here is that in addition to helping with repeatable and consistent code, it helps us in converging to a solution. Now, what you're going to discover is as you get more familiar with different technologies, and also as the problems get more complicated or even complex, that you may have more than one solution. And so for these examples, we're going to assume that there's no more than a couple of potential solutions. And the idea is that we want to systematically figure out which is the best solution for a given problem or project. So one of the outputs or artifacts of the software design process ideally is better software. And what do we mean by better software? Well, one metric for that is better performance. And how can we judge performance? Well, one of the simplest ways to do that is just how long it takes your code to run a given task or a given process. And so, for instance, you could imagine a poorly written code that may run a loop 100 times when it only needs to run it 50 times, or perhaps it takes up more memory than it should because it's allocating more memory for variables that it doesn't actually use. And then another scenario, of course, is that it might take up more hard drive space on your laptop or your desktop. And again, the idea here is that through a systematic approach to software development, you can create better performing software with, of course, less bugs. And what is a bug? Well, you can think of it as an unexpected behavior in an application. Usually we think of bugs at runtime. In other words, the application does something as the user is using it that was not expected. Although you can also think of bugs in your software as being algorithmic. In other words, ones that maybe the user doesn't even notice necessarily, but there's definitely a process that's wrong in the code itself. You can also think of that as syntax problems, but again, those would not survive compile time in a compiled language. But effectively, though, there are any number of reasons why you may have a problem with your code. The idea here is with a more systematic approach, then you can end up with less bugs, less mistakes, less problems with your code. Another one is going to be more reuse. The idea is that maybe you have the same process or algorithm in multiple different locations in your project. The idea is maybe you can sort of factor out that code, put it in a separate function or separate module in your project, and ultimately reuse it from multiple different locations. And what does that get you? Well, it gets you a single place in which to make improvements or changes or bug fixes. And ultimately, that's going to lead to more maintainable code that you can reuse in other projects, and ideally more sustainable code. And sustainability usually is seen in terms of environmental context, and it is oftentimes poorly understood. And we will talk about it later on. But the idea is I want to sort of introduce you to the concept with respect to software development, and sustainability can manifest itself in a couple of different ways, but not the least of which is that the more efficient code that you write, in other words, the code that performs better, whether it's through runtime or better memory management, etc., means that you will require less computer resources potentially to run that code or run that application. In translation, your end user does not have to buy new hardware as often. So again, it probably isn't immediately obvious to you about how sustainability factors into software development and the software design process, but more systematic, more consistent software development leads ideally to more sustainable results. It also helps in documenting a solution. And so one of the easiest things you can do as you go along is to simply keep comments about your code, continue to write them as you go along. What we're going to do is we're going to take a look at techniques about how you would go about doing that. For instance, documenting what a variable does, documenting a little bit about the algorithm that you are using, maybe documenting about which function calls which function, and so on. But you can also document the alternatives, and those alternatives may be working alternatives. In other words, something that you want to revisit in the future. You may simply put a little to do in your code in a comment that tells you what to do in the future. But it also may be the alternatives that didn't work. In other words, future developer can come back and see why you chose the current alternative over another alternative because the other alternative did not, in fact, work. So one of the things I encourage you to do is to refrain from deleting code in your projects, in your programs, but rather initially just start by commenting it out so that it can sort of be a historical reference to what didn't work as you learn better development practices. Also, the documenting a solution as you go along helps with facilitating team and group development. Again, this is about the systematic approach to software design. And when I'm referring to the development of the team and group, I'm not talking about the individual team dynamics, but rather what I'm talking about is when you are working on a large project where you may have multiple people working on similar sections of code or adjacent section of code. And the idea is that you can leave notes in your code for other people who are reviewing your code to help them understand what your thought process was. Another scenario might be that you have to leave a project, and essentially what you're doing is you're leaving your documentation embedded in your code for the next developer who comes in behind you. Or another scenario is simply that the project is so large that it requires multiple developers working on the same parts of the code. So ultimately, all that does is that, again, improves the quality of the code, creating better software, more repeatable, more consistent solutions. And there are many, many, many other reasons why we would want to follow the software design process. So continuing on, let's take a look at a general problem-solving methodology. In other words, this is one that you've probably seen maybe one of your science courses, one of your engineering courses. This is probably the one that you're most comfortable with, and we're not going to spend a ton of time on it. The idea is I want to show how the pieces of a general problem-solving methodology can be mapped to a more software-specific methodology. And we'll just start off by looking at the 5 main parts here, and that is the definition of the problem. Usually that's provided by an instructor, or in the case of software, it would be provided by your client or your customer. That what is this solution supposed to do? In other words, what problem are we trying to solve? Then there's going to be a requirements gathering phase, information gathering phase. Usually that's going to come as the result of asking questions, looking perhaps at how the problem has been solved in other domains, etc. Again, in a more generic sense, then this gathering of information can have multiple sources, followed by the generation of alternative solutions. In other words, you figure out how the problem can be solved in different ways, and then ultimately you pick a solution and then you go with it. The idea, though, is that there's some sort of systematic way of going about doing it, maybe through some sort of weighted tables or something along those lines, where you pick a specific solution out of a range of solutions that could have been considered. And then ultimately you want to communicate the results. Now, this is not a perfect mapping to our software problem solving methodology, but essentially the communication results is the end product for the problem solving methodology. And in our case, it's essentially going to be the end result or the artifact that is given back to our client or to our customer. So to understand a little bit more about the software problem solving methodology, then we want to sort of think now about how that relates to what we just saw, and that we have our requirement specification, which comes from our client developer interaction. In other words, the development team might ask a series of questions to their client or clients. You might get some initial project description of what the client wants, and then you have to meet with the client multiple times. The idea is that you want to sort of nail down then what the client wants, and ultimately that is supposed to be to produce some requirements, some specifications for those requirements, including some things like the amount of time that it should take an application to launch, the amount of memory that is required, and so on. We can then move forward to the analysis phase, which is that preliminary design. Oftentimes, we want to sort of think of this as just extension of the requirement specification, in that we sort of understand the problem, we do an analysis on it, we try to figure out what potential ways we can solve the problem, looking at different algorithms that might work. Best example for this is a search algorithm or a sort algorithm. In other words, which techniques would we want to use? And then what we'll do is we'll design our application around those inputs and outputs and the techniques that we wish to use. And then finally, the fourth step is the implementation stage, which seems kind of interesting and almost a little ironic that it's so late in the process. And the idea is that these first three stages is essentially nothing more than documentation. Now, what you're going to find when we look at some practical examples is that we can do some light coding, but it is essentially going to be nothing more than a combination of comments, pseudocode, and some very basic declarations. In other words, we don't want to really do much of our coding until we get to the actual implementation stage, in which basically what we're going to do is we're going to take all those comments that we wrote, all of the discussion that we put in comment blocks about the algorithm that we want to use, about how we're going to collect the information from the user, and how we are going to return the information back to the user, and then we're going to implement it in the fourth step. Then finally, there's going to be the verification and also a validation step. In other words, we want to check to make sure not only that the program works as we expected it to, but also works as the customer intended for it to be used. And then there's the testing, which again kind of goes in conjunction with that verification and that validation. That testing phase can actually be moved up a little bit into the implementation. We'll talk a little bit more about different strategies when it comes to testing, but fundamentally, those are the 5 steps then in the problem-solving methodology for software. Now, let's start looking at it from a practical standpoint. In other words, we're going to try to simplify this as best as possible so you can get into the habit of writing good code. And the first step is going to be our requirements and analysis. And if you notice from our previous slide, I kind of merged those two. I talked about it sort of as this iterative process where you will be communicating with your client. You'll be asking perhaps questions for clarification. And from that, you're going to refine your requirement specification. But at the same time, then you can also start a little bit of your analysis. And so you can want to sort of think of this as kind of an iterative approach. And then the artifact, if you would, from that is going to be to identify and document using a mix of comments and declarations, the input values and the output values and their types. And again, we're going to see in just a second what I mean by that. I'm trying to give you some practical hands-on examples of this so you can see how you would do this in a real environment. The next step would be then to identify the source and the mechanism, those input values. In other words, are you going to be collecting them from the command line? Are you going to be getting them from a file? Are you going to be getting them from a graphical user interface? Are you going to be getting them from a piece of hardware, maybe streaming the data, etc. So it's very important to understand the source for the data. Now, in the early applications, we're simply going to be using the command line. We'll be using a lot of interaction with your application from the command line, but we'll also be looking at files. Step after that then is going to be to document the necessary algorithms in comments. Notice the emphasis here that this is in comments. So basically what you want to do is you want to choose perhaps your search algorithm or choose your sorting algorithm, not necessarily implement this. So right now your code is still going to look like a bunch of comments, maybe with a couple of variable declarations thrown in, but fundamentally it is going to describe to another developer what you intend to do once you finish this function or finish this application or finish your project. And so you want to include comments about less preferred techniques when applicable, maybe things that you don't think that will work as well, or maybe something that you might want to come back to when you have more time. Probably one of the most common things you'll see in my code is a to-do statement. In other words, maybe I've thought about something, but I want to focus more on just completing the function for now and maybe go back in and do a little more validation later on to look for data that might break my application. And the idea is I'll just simply put a little comment in there that says to do, and it'll tell me what to do then later on. And you want to focus on the concept, not the syntax. So pseudocode is a great way to do this. It kind of looks like the language that you're working in, but at the same time, it's more human readable. And the idea is that another developer can come in behind you, look at your pseudocode and understand what your thought process was. And the best part about it is that sometimes that pseudocode can be used in a completely different language. And so maybe, for instance, that you're working in Java and C#, and the idea is that you've developed your pseudocode intending for it to be used in a Java application, and instead your company has decided to switch to C# and you don't want to start over from scratch. The pseudocode should be ambiguous enough that it should work then in both languages, and of course vice versa. You might start off with C# and then ultimately move to Java. And then the last step in the requirements and analysis portion is to determine the output format and the mechanism. Again, determine how you are going to give the results back to your end user. In other words, is it going to be a command line application? Then you're going to print to the command line. Is it going to be a file? Well, then you're going to need to store the results in a file, a UI, or perhaps even streaming the data over a network. So how do we practically do this now? Looking at the design and the input and the output, well, we'll start off first with designing or creating our input variables, and it is a two-step process. We'll talk more about this in later videos. For right now, I just want to give you a basic understanding of how this works. And so again, this is going to be sort of comments, sort of a mix of comments as well as variable declarations. And the best example I can give you is, let's say, for instance, that you need to calculate something about a circle or something about a sphere. And so you know that you're going to need the radius, you know that it's going to be the double data type. And so sure, you can write that solely in comments, but it's easy to go ahead and create that as a variable declaration. In other words, effectively, you're not going to get much more over creating a comment talking about the radius as being a double as you would just simply declaring it. So again, there's that little gray area where you might find yourself writing a little bit of code early on, but fundamentally that is telling you what you need to do. And so in this case, this is going to be the radius. It's going to be a double data type. And ultimately what I wanted to do even early on is I wanted to point out that you can go ahead and initialize these variables. So it's important that you recognize that the first example is just simply declaring the variable. The radius is declared, however, it is not initialized. In other words, the memory is allocated for a variable. However, the value that is stored in that variable can effectively be thought of as garbage. You can think of it as garbage, or you can just think of it as unpredictable. Either is perfectly fine. I'll sometimes use the term garbage later on in other series, just to sort of emphasize the fact that it is unpredictable. In other words, you don't want to count on what this value is that has not yet been initialized. Now, if you get into the habit of initializing the variable as soon as you declare it. In other words, as soon as you've declared the radius, you go ahead and set it equal to 0. In this case, you could set it equal to 0 or to 0.0 for it being a double. Doesn't really matter because we'll talk about the casting and how that works in a later video. But fundamentally, you now have a predictable value. In other words, you know that the radius is now equal to 0. Now, we'll come back to that in just a second and why that is so important. The next step then is to think about how you want to collect then the data from the user. Now, remember, we already talked about that in the previous slide, is that you should put some comments in saying that, all right, I expect to collect the information from the command line. At this point, then what we want to do is actually implement that relevant data input flow. In other words, actually go through, if it's a command line application, create pairs of lines of code, one presenting the prompt to the user, in this case, a printf. The second one being the scanf that collects the information from the user. Now, again, we're going to get plenty of time to talk about this in later videos. Instead, what I want to do is I want to focus on the comment that comes immediately after the statement. So it tells you exactly what you are doing in this line of code. Now, obviously, this is part of a PowerPoint presentation that is expected to be for new developers. And so you probably want to put something a little more informative in your comment block rather than what I have here. But you can see here the principle is still the same in that you basically document each useful line of code as you go along. And likewise, you do the same thing with the output. So you implement then the relevant display output flow. And you'll notice here I have another print statement followed by a comment that simply says what that particular line of code does. And then continuing with that, then what do you want to think about from a general strategy about completing then your project? Well, once you've got this skeleton in place, in other words, you've declared and initialized the variables, you have the inputs, you figured out that you want to collect them from the command line for this particular example. So you have a combination of those printfs and those scanfs, and you have the outputs, and you have all of this lined up as the skeleton. Then effectively what you're doing is you're going back in and you're filling in the spots between the comments. And so at this point then is where you actually are going through and implementing your algorithm that you chose early on, the equations that you chose early on. And in this particular case, then what we would do is we would go ahead and write a search algorithm, a sort algorithm, maybe, for instance, the physics equations that you'll see in some of the other videos, etc. But notice how this comes so late in the process. The idea is that you want to document as you go along and then go back in and fill in the missing pieces. Now, alternatively, you could go ahead and do all of the inputs first, then the equations and the algorithms, and then the outputs. But I want to point out that if you do the inputs and then the outputs, particularly if you go through the step of initializing all of your input and output variables, you can effectively get the flow of your function or the flow of your application working before you have finalized your algorithm. In other words, basically, you can collect the information using the printfs and the scanfs and ultimately display a table that has the default values to make sure that your customer is happy with how the application actually works, the flow, the presentation, etc. And then you can simply come in and tweak the equations and the algorithms as necessary. Now, again, it's going to be hard for you to force yourself to do this first approach. So if you do decide to flip those last two steps to where you're writing the equations and the algorithms before the output, that's fine. But just consider the fact that you can probably build confidence pretty quickly by creating your inputs and your outputs first, followed by the equations and the algorithms. So again, what are some of the goals for waiting so long to code in general? In other words, why are we doing the algorithms and the equations as the fourth step and arguably into the fifth step? Well, it just helps us with this structured design. An alternative to that is referred to as cowboy coding. It's kind of what you've been doing in the past, where somebody might give you a problem and you would just immediately start typing, trying to solve it, creating variables, working on an equation, not really thinking about the big picture about where that code fits into a bigger project and so on. But you instead want to do is focus on the structure first of your code, particularly as your projects get larger. You'll see that you can actually build the entire framework of your application before you actually do any real coding. And then ultimately it is self-documenting. And why do we love self-documenting? Because I'm pretty sure that none of us like to go back and document what we've done after we're finished. In other words, we're relieved to just simply get it done. And we'll say, oh, we'll come back to documenting it later. Well, if you follow this more structured approach, you kind of get the documentation for free. Now, there's a couple of other tricks that we can talk about, including good variable names mixed in, that will help with that code to make your code more self-documenting. But again, if you follow this software development method, this software development process, you will end up with better quality code, better documented code, ideally better running code, less bugs, all of the things that we talked about earlier. Now, the good news is I have some practical examples that will follow this video that talk about how you would actually go about doing this. So again, what you want to do is you want to think of this now big picture wise, how would you do this with any language? And then what we're going to do is we're going to focus in on specific languages. So as always, if you have any questions, comments, or concerns, don't hesitate to reach out to me. And thank you for watching.